Any sufficiently advanced technology is indistinguishable from magic.
Today we're talking to a preeminent cosmologist, a thinker, a motivator, an inspiration, and also my best man at my wedding. But today we're going to talk about him, and that's Professor Stephon Alexander, my oldest friend, pretty much, and really, as I say, an inspiration. How are you doing today, my brother Steph?
Hey, this was one of the many interviews that I'm looking forward to.
I hope not that many, but
one of the few of many. Let's say
you're going to say like top 20 interviews of the week, of the day. Well, you deserve all the rich success that you are engendering, and that is, of course, Stephon Alexander, author of previously The Jazz of Physics, and now Fear of a Black Universe. And that title we're going to get into in the cover of the book. Cover of the book's not as interesting as Jazz of Physics, at least visually, but the content material is just off the charts. I can't really give you the acclaim that you deserve, Stephon, because it's such a great book. It's so well written, and it is really going to open up new horizons. But before we do that, before we get into the meat and the guts of it, the title is inescapable. As soon as I heard it, I was like, damn, why didn't I write that as my book? No. But I love Chuck D, and I love Public Enemy, Flava Flav. I've loved them for decades. You know that. But I could never get the encomium. I could never get the blurb that you got. I'm going to read it here from none other than Professor Chuck D, rapper and co-founder of Public Enemy, who says about this book, the rabbit hole gets wrestled here. An old school saying applies. The more you know, the more you don't know. That's really old. So that's like Aristotle, man. Dance along this, read into the unknown, and find out that this book may be the best ever answer to what is soul. And I'm just wondering, man, do you want me to read what Chuck D said, what Flavor Flav said, rather?
Yeah.
He said, yo, boy, what time is it? It's time to read Fear of a Black Universe. And he's got the huge, no, he didn't say that. Yeah. Brother Stephon, tell me, what does this mean? What is Fear of a Black Universe? Where'd you get the name? Where'd you get the subtitle? An Outsider's Guide to the Future of Physics.
Yes. Well, there's a funny story about that. And like, if you allow me. So you've written a book, you're losing a Nobel Prize, and you know that finding a good title is like tough business, right? Because, you want to draw the reader in the books, they're in the books, they see the book, and the title can draw them in. So anyway, make a long story short, my editor, TJ Kelleher, kept bothering me. What's the title of the book? I mean, this is in the middle of writing my book. I don't have a title yet. And at some point, I kept coming up with titles, and the titles were corny. And they were, like, I'm not even going to waste time telling you how corny some of these titles were. And he kept coming back, and the marketing team kept coming back and saying, nah, that doesn't really cut it. Nah, that whatever. So one day I actually I invited TJ to come to Brown to give some talks to different, colleagues about writing, potentially book deals and things like that. But it was an opportunity for me and him to really hang out and talk more about the book. And I took him to this Irish pub in Providence. And it was like this is like pre-COVID. This is like a couple of years ago. And I took him to this pub at late at night. And, we're having a few brews, And at some point, I decided, and you've known me for a long time, I suck at being sarcastic. It's just not me to do that, right? I was like, I'm going to be sarcastic here. And I said, TJ, I got the title of the book for you. And it was designed to just be a spoof, right? It was a joke. I said, Fear of a Black Universe, man. And anyway, I left that behind. And then a month later, I get a text from him. He goes, that's it. I met with the marketing team. They love it. And I was like, really? So anyway, that's but the truth of the matter is actually, after some reflection, I realized it was one of these intuitive types of things, right? That deep down, the book is about the title it's a combination of things, right? in one sense, there's ambiguity to it. In one sense, it's like, well, when we think about black and the idea of the category of blackness, and that which that which is misunderstood, right? Ignored sometimes, invisible, and stigmatized. I mean, so when we think about even our laws, like black body radiation was misunderstood for a while. Black holes, the singularity, right? The event horizon, what's inside, dark matter, dark energy. So we tend to, in physics, just not give names like that to dark this, black this, for things we don't understand that are mysterious. It's a placeholder for those things sometimes. Also, I just think when we think about like society and sociology and psychology, the dark, we're afraid of the dark, right? When we think about blackness, the American notion of being black. When I lived in Europe, I realized that white people out there even created their own categories of the stigmatized, being stigmatized, right? And having also black ideas that could actually get you in trouble, right? And so you might want to, if you have as a physicist maybe an idea that is so out there and crazy, it may, your colleagues may write you off and kick you out of the club. They won't invite you to reindeer games and these kind of things, right? You won't get invited to a conference. So there's a fear in that. So I think like in that sense, but primarily it really was a nod to Public Enemy, because I grew up with, I grew up in the Bronx, right? Not too far from where you grew up. And in the 80s, and Public Enemy, I used to wear, African medallions and things like that, all throughout college, right? One of my favorite lines, I think, was from Welcome to the Terror Dome on the album Fear of a Black Planet, was, I got so much trouble on my mind, refuse to lose. It was, I got trouble on my mind, man, but I refuse to lose, So it was a nod to that time of my life, and also an acknowledgement that, despite the fact that some people will say, I have the subtitle, The Outsiders Guy. People say, you're not an outsider. You're a full professor at an Ivy League school. But there was a part of me that was like, no, I still choose, in a sense, to acknowledge the outsider in me, and celebrate it and see it actually as a positive. So the book was also a celebration, not a complaining, okay, and not a woe is me, I'm an outsider, but actually here are the hidden advantages actually to being an outsider. So the book kind of goes into that as well. That's my long-winded kind of answer.
That's your long-winded short story. But my grandfather invented Cliff Notes, right? And I asked him, how did he do it? And he said, well,
For real?
He said, let me make a long story short. No, I'm just kidding. That's an old joke.
You got me.
One of the other cover encomia and blurbs that appear on Fear of a Black Universe comes from our mutual friend, the now president of the Simons Foundation, Professor David Spergel, past three-time guest on Into the Impossible. You're a four-time guest on Into the Impossible, so you still beat Brother David. But he said this book is effectively a sequel to A Brief History of Time. Now, I remember meeting Professor Stephen Hawking in London in 95, 96, when we were both hotshot young grad students at Brown. You were hotter than I was, but anyway. And there was a question posed to him.
Okay, go.
You actually, by the way, I got to give you a shout out. Without you, I wouldn't be drinking the beverage that's in here right now, which is coffee. You introduced me to coffee at age 21, 22, whenever we met. And we used to go to Ocean's Coffee Roaster. Shout out to no longer pour some coffee out on the sidewalk, right? But Brother David Spergel says this book compares to A Brief History of Time. Now, when I heard Stephen Hawking asked, why did you write Brief History of Time? He said, because I needed to pay for my daughter's college tuition. And I always thought that was kind of silly. Now, I know you've got a lovely daughter, but that wasn't the reason you wrote this book. But how does it compare to Brief History of Time? Why is it, as I believe the case to be true, a worthy successor to that most famous of all popular science books?
Yeah, it's really funny. And it was probably the biggest compliment that I think any science writer, physics writer could ever get. And I don't know if I'm allowed to say this, but let's say David Spergel is one of the most important cosmologists on the planet today. And so coming from him was a big deal. But also, he was, I think it's public knowledge maybe, but he was offered the Lucasian chair. He was offered Hawking's position. So who better to come from than him, than David Spergel? Again, that's a conjecture. I'm not certain that was the case, but in fact, check that. But either way, my point here, maybe he was being considered for the Lucasian chair. That might be the more correct way of saying it. But either way, the first science book I ever laid my hands on, and it was given to me, I was, at Dewey Clinton High School in the Bronx, New York, 6,000 students. We had, it was roughly 60% dropout rate, but this woman, her father went to my high school. His name was Barney Sharon, Sharin. And Susan Sharon wanted to kind of reach out to promising students and give a scholarship, an academic scholarship in her father's name, Barney Sharon. I think, Stanley also went to my high school. Peter Lifshitz went to my high school, right? Make a long story short, but anyway, and she gave me this book as a gift when I was 15 years old, A Brief History of Time. And it's funny because I actually have my copy of A Brief History of Time still here with me. And of course, I just wanted I was actually talking about it the other day, so it was it's here. But anyway, and it's one of these things where when you're writing, you don't realize the impact books, really important books, are going to have in your writing. So I actually deliberately, when I was writing this book, wanted to write a book with a similar type of format as A Brief History of Time, and another book, which is A Character of Physical Law. And so let me give you an example of what I mean by that.
And that's by Feynman. That's his
messenger. By Feynman, yeah. The Character of Physical Law.
Yeah.
So in Feynman's book, he wanted to kind of spell out, thinking about physics in terms of principles, that maybe we can just think about maybe the simplest principles and explain much of physics with these principles. And I wanted to play a similar game here, but I wanted to use these principles. I wanted to do that to liberate the reader from jargon and the mess of complicated equations and things like that. I wanted to say, okay, if we can tie down these three principles and really explicate them at the beginning of the book, then I can use that as a basis or as the ingredient and the basic ingredients to then talk about, for me, the most pressing and the pressing questions on the horizons of the field of fundamental physics, cosmology, particle physics, and quantum gravity, and unification. So I wanted to kind of riff on that in the same manner that Stephen Hawking did. And remember, one of the things that really fascinated me and really hooked me on Hawking was, he asked he did go there. He said, I want to know, did God have a choice in creating the universe, right? And so he also discussed matters that maybe we were taught not to discuss in our education as physicists. And so likewise, I did similar things. I talked about, I gave myself the liberty to talk about questions about life and consciousness, and some aspects of spirituality, but not veering too far away from the basic principles that the book, establishes at the very beginning. So it's in that sense. So I was not surprised. I didn't tell David when I gave him the book to read, when the book company gave him the book to read, that the book was inspired by Hawking. He read it and inferred that on his own. So that to me was very pleasing.
Yeah, I have to be honest with you. There are a lot of books that have come out lately from colleagues of ours, that talk about experiences of African Americans and other people of color in science, et cetera. And from the title and maybe even from the outsiders, I thought that's what it was going to be about. I mean, as they say, don't judge a book by its cover. But on the other hand, what else do you have to judge a book by? It's like we have to be Bayesians and look at analysis with the data that we have. And so even though knowing you, I thought it was incongruous, because I didn't think you were going to take that tack where you would say, this is the experience of a Black, man in America, in the Bronx, coming from Trinidad, immigrant story, all the stuff that you've been through. And it really wasn't about that. I mean, Jazz of Physics was more kind of autobiographical. This is kind of, I call this, kind of more like a flight plan. As a pilot, I'm a pilot, right?
Yes, yeah, no, that's a good analogy, actually.
You remember when we flew together, Steph?
Well, I have very good memories of that, especially when we got serious weather, and I was like, okay, this guy's going to navigate us through this, okay.
This guy who, first taught,
right. This is where I'm going to choose to die.
That's exactly right. This guy who can't, clean up a plate after he cooks it at the house is going to take me on a flight across the Rhode Island Sound there. No, it didn't. It worked out okay. We're both here to talk about. But I see it as a flight plan. Where can physics go? Where can things like consciousness go? Where can things like aliens and dark energy and the greatest mysteries? So I want to say, normally you hear questions like this to an eminent scientist like yourself. Normally I'll ask, what got you interested in science? What inspires you? I don't want to know that. I I already know that, by the way.
Yeah.
But I want to ask you, as a scientist now, not as a kid, what is your curiosity burning brightest about?
Yeah, that's a good one. I've always had, you knew that when I was a grad student, we were grad students in the same year, I was always, when Penrose had his theory with Stuart Hameroff, remember, about, his theory about the mitochondrion being the harnessing quantum information to speak about consciousness in the brain. I went to Humphrey Maris, who's an eminent experimental physicist. And I said, and I made a case to Humphrey that we should do an experiment, like a laser experiment with, by studying basically the waveguide properties of mitochondria, like to see whether or not, you can have quantum coherence. So I was already I already had this kind of fascination with the connection between physics and biology and life, but at a more deeper level, not at the level of atomic bonds and like chemistry, which already is a connection between quantum mechanics already and life, because you need quantum chemistry is about bonding structures, right, and valence shells and all that good stuff. That's quantum mechanics, and you need that to talk about proteins. But the more weird things about quantum tunneling, these other weirder things, quantum entanglement, right? These other categories of quantum mechanics that's even more bizarre, and whether or not these things had something to say about life. I already was exploring that, but of course, the importance of writing papers and following the herd and getting a good postdoc, and that bug never left me. And I think this book was my way of exploring that. We write books sometimes to kind of explore and better articulate things that we have in our head, and it's an opportunity. It's one format that we can, explore these questions. And so the book was, let me stop talking. My fascination these days is, okay, given, what we know about cosmology, we know about dark energy and dark matter and cosmic inflation, maybe the theory of the early universe, where space-time might emerge. Is space-time an emergent property? Is it something else? And whether or not, where do we see hints of life and consciousness interpolating those mysteries, right? And the book does explore some of those questions and speculates on that the same way, in the same spirit of, say, how Feynman ends his book in The Character of Physical Law, or Hawkins' A Brief History of Time, as two good examples. By the way, very tough acts to follow, and the jury is out. I don't think I owned up to it, but it was an attempt. So we'll see where it goes. But I end by saying some crazy stuff. And the black horse was my fear of coming out and just saying that. And I think that, going back to the idea of I think the idea of okay, I'm a black man or a black person doing physics, right? At this level, what better way, right? What better way to express that than to really go there in terms of theorizing, right? So I don't know. My point was to sort of let me tackle some really, really hard questions in this book. Let me speculate, and let me not be afraid of being wrong or even chastised because of it. Because guess what? That's sometimes what it means to be, to live in a world where you're already stigmatized. And so what fear do I have? It already happens to me, So that's one riff.
And I wonder, if you could comment on, because you must have this happen a lot too, where, I note on my videos, whenever I post a video that's about cosmology or about string theory and things like that, I get comments such as, the following, that big bangs in an oscillator flow or spiral cosmological model, my friend Roger Perlman, et cetera, et cetera. So I get all these comments and, they're completely unorthodox. Space is finite. The Big Bang never happened. Time is infinite. Everything emerges from, a quadrupolar pair. I get a lot of, refreshingly candid new theories, shall we say. Yes. I never see experimentalists, I never see like, oh, well, here's an experiment, except nowadays I start to get people wanting to investigate UFOs and things like that. And so they are proposing observations and I'm involved with some of these things. But anyway, the point is, how do you...
come see me. I got a lot of aliens I can point them out to.
So how do you draw the line? Like, because there's only so much time in the day. You need to apply a low pass filter and block off your time. How do you know, like, when someone's an outsider, like a Nikola Tesla or somebody like that, destined to change the world, or an Elon Musk, or even an Einstein? Before he was Einstein, he wasn't Einstein, as our mutual friend Jim Gates always says. How do you know someone's an outsider versus being totally out to lunch?
That's a good. Let me see if I can address that with the following notion. And one of my heroes, and probably my biggest hero in physics, in terms of personally, is Leon Cooper, Nobel Prize winner for superconductivity, and of course, and I discuss this a chapter where I talk about his description of his discovery to me when I was a graduate student. So when I was a postdoc, came back to visit him, and I think this captures it. But one of the things that it occurred to me with Leon in the many years that I've known him, almost 30 years, as long as I've known you, since we both knew Leon when we were first year graduate students.
That's right.
In fact, both took advanced quantum mechanics with him. Remember that class?
Oh, I remember it. Yeah, he told me I didn't learn my undergraduate quantum mechanics well enough to ask him about negative energy states and the Dirac equation. Anyway, he did so very gentlemanly, and then I teased him. I said, "Well, I learned quantum mechanics from your textbook, Professor Cooper." No, I didn't.
Well, Leon, the thing about Leon that's weird, that was crazy, was that I was in that class. I used to sit in the back of the room, and one time I said what I thought to be the most idiotic thing, and he was like, well, that's a really good question. And so he was kind of one of these rascals.
Right.
Yeah, right. So he'd get you. So anyway, but one thing I learned about Leon, right, was like Leon knows so much, right? But the thing that was interesting about Leon was that Leon was not interested in talking to other people that knew what he knew, right? Because he was so smart. He just knew so much science. Forget about just physics. And so his interest was also talking to people that knew things he didn't know. And so this balance, I think you need both. I think you got to be grounded. I think one of the things I try to do in the book was to ground the book. Like it really, I thought I did a really good job in really describing quantum field theory in terms of mode oscillators and as a combination of special relativity and
the illustrations are killer. I mean, I'll show you
the position principle. Yeah. Thank you.
I mean, the field ones. I got one of my daughters was she went crazy with the highlighter on one of these.
Oh my God! Could you send me a picture of that?
Yeah, I will. That's the review on Amazon. Leave it on Amazon.
Wow! That's like I met her when she was a little baby.
Yeah,
so that's amazing.
Right.
So I gotta get a picture of that.
Anyway, the analogies, the visual analogies are so on point that it really. You never dumb things down. I mean, you go into some serious stuff with string gas cosmology. We're going to get into that later. That's one of my favorite chapters. But you never dumb it down. And I think that's a sign of respect for your audience. And the courage that you have to do that, I think, comes from this upbringing. Plus, you have a natural gift, I would say. I think you wouldn't dispute that, right?
Yeah. Thank you.
Yeah.
I mean, I don't. It's hard for me to accept what you call compliments, but I thank you. I'm learning to accept compliments from time to time because. Um, but it's interesting. Let me say another thing. It just occurred to me. I growing up in the Bronx. I think one of the things that let me say it another way. I grew up in an era. This is the first time I'm saying this publicly. Actually, I don't know if you knew this, but I was part. When I was 17 years old, I was approached by some friends of mine to join a hip hop group called Timbuk 3. And that was part of Native Tongue. And that group, we used to go to Strong City Studios up in Alton Avenue that was run by Africa Bambaataa, Jazzy J, and Rocco Bucano. And I used to, be in that studio with Jazzy J and my friends who were part of this group. I was not a rapper. I was a beat maker. I used to sample my saxophone, but I was very much in. And here's the thing that's really interesting. Like when we were sampling and we were taking elements to make beats and make music, we would just draw from anything. So the most obscure records, like Walt Disney records and like all kinds of obscure things, we would basically take these elements and bring them together. And the art was actually making it sound good, making it funky. And I think that I was, when I look at some of the papers that I wrote when I was a postdoc and I was maybe made fun of for the string theorists would say, the loop quantum gravity people are loopy, don't even pay attention to their theory, and vice versa with other things. And when I look at some of my papers, it didn't matter to me. Like, what if I found useful, just like a mixologist or, doing a remix or, as a beat maker, a hip hop beat maker, the point was like you wanted whatever work, whatever tools would work to make something coherent and do something that's scientifically sound, even if it meant making a prediction or connecting to experiment. I didn't limit myself. There's another word. I didn't self-edit in that way, right? So I think that going back to your question about, where do you see where's the dividing line? And I think you need, I look at it more like you need to be grounded and know and have your skill set, and it's a lifelong process as a scientist. Okay, just like as a saxophonist, it's learning to play the sax is a lifelong thing. I can always get better at that, but I'm not going to wait until I become John Coltrane to try to do something creative. And so to answer that question, I think it's important to put ideas out there, populate the landscape of ideas, right? I think this is also inspired by our friend Eric Weinstein, and then let people then shoot it down. Let experiments shoot it down. Let's not self-edit these ideas, and let's keep an open mind, and then use our methods and our techniques and mathematics and experiments to then say, okay, this is right, this is wrong. No one has ever died from theorizing. Maybe they've didn't get a grant proposal funded, but.
You end the book on that note. Nobody died from theorizing, and that must be from Abhay Ashtekar. Wonderful, your former fellow colleague at Penn State. But the concept of theorizing in public has changed since the time of the masters that we look up to, even Hawking, even Feynman, et cetera. And I like to use a thought example. Imagine you go back to 1864. In the UK, in Scotland, there's a guy by the name of James Clerk Maxwell. And he's got all these ideas. He's got ideas about the electromagnetic field and equations that will bear his name and later be made into a version that Frank Wilczek, our mutual friend, calls the Maxwell equation on steroids in the Yang-Mills version that you talk about in this book. And but he's working on it, and he's like, oh yeah, well, how do these field theories work? How do these waves oscillate? What do they oscillate in? Oh, well, there are these gears and whirlpools in space, and there are these vortices. He would have been laughed out of his mind, right? People would have tormented him. They would have said he's ridiculous. And guess what? They would have thrown the baby out with the bathwater, and we wouldn't know about Maxwell to this day. So is there a hindrance now with theorizing in public, as Eric has done, and as other people, Carlo Rovelli, who's been a guest on the show many times, even Lee Smolin, your colleague and friend, endorser of the book. The situation has changed. Our mutual friend, Paul Steinhardt, he refuses to go on Twitter. He refuses to go on social media, and he's got his own, kind of bold outsider-like prediction. So I guess the thing I came away with is you can be an outsider even if you're an insider, because there are enough people out there that are trying to gun for it, take you down, do whatever. But speak about that, the courage of a theorist, because I think, in a certain sense, theorists are more courageous because they can put their ideas out, but experimentalists are more bold because they actually have to test it. And there's an old saying: a theorist only has to be right once in his or her life, but an experimentalist has to only be wrong once in his life or her life. Of course, I proved that wrong, right? I was wrong, and I still live to tell a tale. But anyway, what do you make of this? Does it take courage to do what you do, or is it like, I'll throw it out there, it'll probably never get tested, so what difference does it make?
Yeah, I think that if you want to play safe as a theorist, I don't want to use the word. The best description I have is follow the herd. There's a shepherd and there's a herd, and if there's certain influential people. Or by the way, nowhere am I saying that there's anything wrong with this. I'm saying that one game you can play is to just follow the herd and follow what's fashionable and what other people are writing about. And guess what? I did that too. When
who is the herd? Who is the shepherd?
Well,
and who is the herd in this?
I remember it was it's still. When I was a postdoc, string theory was very fashionable. People were writing papers on brain worlds and high dimensional realizations of cosmology, and I wrote papers on that too.
Yeah,
and it was
highest cited papers.
Those papers got cited crazy.
Yeah,
I got hundreds of citations from 2 such papers that I wrote. And I learned a lot, by the way. I learned how to calculate in higher dimensions. And I picked up skills and skill sets and intuitions and all that kind of stuff. It was all worth it. One of my great mentors, the late Joe Polchinski, said, string theory is going to be useful for something. And I agree with that. It's technology, and it might still end up being correct at the end of the day, okay? So the jury is still out, actually. I wrote these papers, and it got me a great postdoc. It got me 2 great postdocs because I was writing papers on that and not on loop quantum gravity, where there were few jobs and available at the time, right? So again, that's one model, right? And of course, I'm obviously simplifying this, so I'm open to scrutiny, right? When I'm saying this, I'm definitely deliberately simplifying things here. But then, if you're really going to aim for something maybe big or bold, I think, I guess the thing here is that if you have an intuition or a hunch and it stands outside of what's fashionable, I say, the whole point is, I think one way of doing this is to say that when I was under my second postdoc, my postdoc advisor, Michael Peskin, used to just basically shut up and calculate, not directly, but it's like, go away, just calculate this thing and come back to me in a few weeks, okay? And I remember at some point I was very frustrated. I was like, man, why is this guy put me through this? Go do these loop diagrams and come back. It's like, why does this guy put me through this? And one day he said something to me that blew me away. He just out of the blue, he goes, you're doing this so that you can master the stuff and then use this to do what you want to do with it, right? So it's just like, it sounds to me like, learn how to play the saxophone really well, learn the techniques, go through all the etudes and the scales and the theory and all this stuff, right? Get it under your finger, not so that you can play memorize the solo of John Coltrane, Giant Steps, but so you can make your own stuff, right? And so it isn't just to say like, I'm going to go and deliberately have some audacious, crazy idea that's woo-woo, but it's more like you do the hard work, you do the stuff, you engage in conversation, you have soundboards, right? And if you get lucky to have an intuition that is on the outside or is that you're like, oh my goodness, like if I say this, my colleague's going to laugh at me. what I'm saying is go for it, and then use the techniques and the math and all this stuff, the tools that you've developed to help refine it into something that is communicable and might even connect, hopefully, with experiment. So that's kind of where I was trying to go with it. It's a dance, and I don't claim that I know the complete answer, but the book, in writing the book, I was exploring that. Let me also say one last thing about this too. I mean, I think one of the best examples is Michael Faraday, right? Because Faraday, first of all, was an experimentalist. I guess he was not supposed to be theorizing, but he had his own theory about invisible lines of force. Well, how woo-woo and witchcraft do you want to get there, right? During that time, the 1800s, I mean, like, if there was a stake to be burnt at, to say there's an invisible lines of force. And he was a laughingstock. I mean, his idea was called idiotic, and the fundamental paradigm of our physics is quantum field theory, or fields. Everything is made up of fields. So that's, I think, one of the great ironies of, I think, what I'm talking about. But it's really hard to say, how do you actually do it?
Mm-hmm.
Yeah. I mean, and what I do in the book is tell stories. I try to communicate that instead of explain it away, but like by telling stories. So the book you'll see a lot of stories of different surprising things. Schrodinger's reading of the Vedic philosophy, and Niels Bohr, and Pauli doing dream analysis with Carl Jung. Mr. Ultimate Insight is saying your theory is not even wrong.
Right.
It's like engaging in dream analysis.
Yeah, yeah, and those guys were buddies, right? So
Right.
Pauli and his friend Carl Jung. Yeah, we had Paul Halpern on last year to talk about their unlikely relationship synchronicity. Yeah, I remember you talking about all that stuff the first year. And there's always a danger because like you're telling me their woo woo stuff, and I'm kind of like in my mind shooting the message. I'm like, why is this guy into like the orgone and the like Vedic stuff, and then like all of a sudden it comes, well, not the orgone, but anyway, everything comes full circle.
Right. Remember I had that thick book on the desk? The orgone energy. Oh my God, that's crazy.
I came in there, I was like, are you reading like Gradstein and Rizhik? Like, no, it's like the Vedic, Contra Vedic, I don't know. I never got too deeply involved in that, but I always thought, this is kind of out there, but you need that because it is the outsiders. And it's not just like diversity for, let's get real. I mean, it's not like diversity as your friend of mine, Jim Gates, always talks about. It's like, if you're not diverse, it hurts you, the non-diverse one, who's just like keeping things in like, it's going to hurt physics if we don't have a certain perspective. That's different from our traditions because, we're still all kind of living off the fumes of Isaac Newton and Albert Einstein, et cetera. And some argue, like Sabine Hassenfelder, our mutual friend, that fundamental physics is kind of stagnant in some sense, although many people find that controversial. But, in this book, you get into something that actually Sabina is now working on, which is like superfluid dark matter. And that to me is like the ultimate, like totally out of left field. That combines your early work with Leon Cooper and his obvious Titanic contributions with a new method of applying condensed matter physics to cosmology. So that only could come from an outsider. Talk about that theory, your theory, and the work that you and your colleagues are working on about superfluid dark matter. Yeah.
And in fact, that was a good example. That actually started with Leon. One time I was in his office. I went to visit him. At the time I was at Penn State. And so I was driving up to Boston for some reason, maybe to give a talk, and I popped into Providence and to see him. And then he sits me. We're in this, remember his huge office, his office, and then he tells me. So I was telling him what I was working on, thinking that I was telling him something clever, and he goes, "You know what? You need to find a real problem and do some real physics, okay?" And he goes, a lot of people in your field. They stop working on the hard problem because they say that like physics is stagnant and all this stuff. You know what? They're just scared. They're scared to solve a problem. When people thought superconductivity was impossible to solve, it was solvable. We solved it. Okay. So you know what? Find a real problem and go solve it. And I was like, you mean like the really hard one? Like, these problems, like the singularity, all these things. He goes, yeah, find a real. He goes to the blackboard and he goes, I'll give you an example. He goes, people say that the Big Bang, the singularities are it's impossible to get around. But let me show you something. And then he literally does a geometric series, like a resummation, and shows that what you thought was a singularity in a function, right, could be resummed and it's not singularity. And I was like, wait a minute, that's actually really interesting. And that got me thinking about taking some of the ideas that he had in superconductivity, which has a semblance of the same type of quantum mechanics, many-body quantum mechanics, in superfluidity, like for example, superfluid helium, where the helium atoms, in a sense, Cooper pair, right, to go into the superfluid state. And the idea was, our idea was basically to think of, with the modern version of the idea, which is work that I did with my former postdoc, Evan McDonough, and David Spergel, was that we said, the idea was that in the early universe, you have, it's the thing that's Cooper pairing to form like a superfluid, are dark quarks. So you have quarks that are produced during inflation by a mechanism that we spelt out, usual particle production mechanism of cosmic inflation. But what happens is that this is a strongly coupled phenomenon, and akin to some color superconductivity ideas that Krishna Rajagopal and Alfred and Frank Wilczek and others developed. That you can basically, it's very much preferred. The cosmological dynamics at very low temperatures, instead of these quarks forming a thermal state, they actually, there's an attractive channel and they Cooper pair up to form a superfluid. And so the idea is that the dark matter in this case is a superfluid made up of these dark quarks. That is different than the superfluid that we find in bosonic particles, like an axion, like ultralight axions, can also do a similar thing. And they're distinguishing observables for these two different types of superfluids. Yeah, but the basic idea is just like, think of a superfluid in a bucket and fill out the universe with this superfluid, and it has properties very similar to that of what a dark halo could have. And in a recent paper, we actually showed that you get very naturally stable dark halos made up of this superfluid. And it has certain predictions having to do with excitations. Like in a superfluid, if you rotate it, you can get excitations called rotons and vortices. Yeah. Well, you'll get these types of objects in halos. You can have substructure that will look like line-like defects. And one of the things we're working on right now is to actually look at basically what kind of observables you'll see through like things like gravitational lensing. One final thing, there is some connection to chiral gravitational waves in this. I know that's something that you've, as director of the Simons Observatory, you guys are thinking about. But we can talk about that offline.
Yeah. This is about your book and your ideas. And one of the ideas you talk a lot about is a very provocative idea, I would say, and that is, the origin of dark energy might be kind of the waste byproduct of events.
That was woo-woo.
And that's with your buddy Jaron Lanier, the inventor of virtual reality, a brother that you introduced me to up in Northern California one day in his treehouse. Wandered through there. Love to get the two of you guys to chat about your recent paper together.
We'd love to do that. We'd love to do that.
Yeah, I had Leon over the summer, and he mentioned that you guys were leading that effort. But anyway, you guys had this. I have to say, it is literally far out. So talk about this idea. What is the dark energy? I mean, first of all, why is this a problem? Like, in nature, we're always trying to explain things. But as Feynman says in Character of Physical Laws, you noted, at the end, he's just like, well, it might be that nature has an infinite layer of onion skins. And the pleasure of finding things out is just peeling away a couple layers, not like getting to the center of the onion. What do you have then? You don't even have an onion ring. I mean, that's like nothing, right? So talk about that. Why is it why do we need to figure out what dark energy is? Well, what's the big deal? Yeah,
that's a very good question. So let me say that what I'm about to say here is coming from a place of ignorance ultimately, because if I was able to articulate what the problem really is, then I'd probably be close to solving it, right? And as a big part of writing this book too, is as a practicing theorist and physicist, right? And the always reason I love talking to bright experimenters like you is we're in the process of trying to understand what the problem is. Because once you understand the problem, more clearly, then you might have a go at tackling it with or going beyond it, and or to even realize that there was no problem to begin with. So the way I would like my in with dark energy is to think. Oftentimes, it's usually formulated as, "Oh, the universe is accelerating. The expansion rate of the universe is accelerating," and that is one aspect to dark energy, because the way that feeds in to Einstein's theory of general relativity is that if you have a form of energy that has negative pressure equation of state, like a baryotropic equation of state that's negative, then you get this repulsive effect, this accelerated expansion. But there's another side of the dark energy problem, and that is that what's doing this is something, a form of energy momentum or energy, let's say, that's feeding into into space time. That's sourcing this, and that thing actually is indistinguishable from something called a cosmological constant or vacuum energy. These words are interchangeable. And so what does that mean? It means actually we don't have to go all the way to outer space to talk about dark energy. Take a tiny bit of empty space right in front of you, the same space in front of us. There's the same space way out there. And this space in front of us, there's energy associated with empty space. So this vacuum energy is actually, if I take a cubic centimeter, right, there is a tiny bit of this vacuum energy in this piece of empty space. And people like Richard Feynman, right, and his predecessors and contemporaries taught us how quantum field theories, okay, how interacting quantum fields can generate particles coming into a virtual particle, an electron-positron pair coming in, and then annihilating very quickly. That process will generate some of this energy in empty space. And we have many of these processes that we can calculate in our standard model with the same precision that we'd go to calculate the G2 of muon, for example, right? All these precision things that we calculate in the standard model, and we go measure, the same precision predicts actually that empty space should have way too much vacuum energy than what is actually observed. So the question is, where is it hiding? What do we need to what do we need to do to our standard model, our precision standard model, to get rid of this vacuum energy? So the idea, the part of this cosmological constant dark energy problem, if I can summarize it, is that we know that there's vacuum energy that's making this universe accelerate, but there's way too little of it per cubic centimeter than what we should expect by our very precision, the most precision theories that we have. Quantum electrodynamics, for example, the standard model, right? So the question is, what's going on between how the standard model speaks to general relativity that's causing this huge discrepancy between what we observe and what the theory is actually predicting. There should be way too much vacuum energy in a piece of empty space in front of our faces. Where is it? And that's one way of maybe characterizing the dark energy / cosmological constant problem. Mm-hmm. Does that help?
Yeah, absolutely. Now, if I told you, Stephon, that the cosmological constant, we just got an update from past guest on the show, Adam Rees. He said, actually, no, you know what? It's more consistent with a cosmological constant with a positive equation of state. And, it's not really a cosmological constant at all. It's more like, matter, radiation, something like that. Wouldn't you throw out your theory? I mean, the thing I'm getting at is that, we talk about string theory, and it's been around for a long time. And you and I were there during some of the big revolutions you talk about in the book on Maldacena. That was happening right as we were graduating around then, 2000-ish. And ADS CFT. And lately I've been doing a lot of videos. I had a video out last week by the time this comes out. And it was about, what is the minimum that string theory has to do? In contradistinction to Lenny Susskind, who was a guest on the show, he has these books, The Theoretical Minimum, Well, I'm
Great
thinking,
book. Great
what's
books.
but what's the experimental minimum? In other words, if I tell you, that this only works in a positive, anti-de Sitter space, not the Sitter space like we live in, shouldn't you just stop working right now? I mean, like, why do they keep going with it? You talk a little bit about, ADS CFT. Why do people even talk about string theory if it predicts, the exact opposite behavior in a negative cosmological constant? And we know the universe has a positive, dark energy, if not a cosmological constant.
Yeah, I mean, so that's right. So I think one of the things that theorists do is that we work with things called toy models, right? Remember Brandenburg said we have a toy model. We have a pencil to talk about something standing on on an idealized surface, and it falls. And anyway, so we tend to have toy models. So I would think of these solutions that are given to us in string theory, where a negative cosmological constant is preferred as solutions of the theory. And so, yeah, I mean, by studying those solutions, those toy models, they hope to gain more insight into the real deal, where we get a positive cosmological constant. And I think I like the work that string theorists, some of them are doing, where they literally break the theory. They literally, they introduce a cosmological constant in some really, not contrived but very elegant ways. And I'm a big believer in it's important to break your theory, meaning that whatever your theory is, and if there are underlying principles that govern the theory, in this case, in string theory, there are certain symmetries at work that you try to preserve in looking for solutions. And if you break that, then usually you break some principles in the theory. Like, the bad one, of course, is if you break unitarity of the theory, right? So anyway, the point here is that, or you reintroduce anomalies into the theory, things like that. So, but I think it's useful to have toy models, and then once you gain enough experience, actually jump in it and try to make contact with the real world. Our job, I think, as theorists, is to, it's our tradition has always been, when Einstein discovered general relativity, the perihelion of Mercury. And then people were looking at cosmological solution. Lemaitre, right? Found the first. I think he was one of the first to find to talk about the conic cup. The day yesterday, whatever. The day before there was yesterday, whatever the saying was. The saying. But anyway, my point is that there's always been a tradition where no matter what kind of theorizing you're doing, behind it there's always a standard and an ethic to try to connect as best as you can to observations, and especially to those that cannot be explained by current theory.
Yeah, and that's certainly true. And in fact, in the video that I made, I'll link to it in this video, I say just that. I say, it was important, and it's fine to be guided by what Einstein did. That was a retrodiction. In other words, he's just explaining, which is huge, that which Newton lacked. But he also had all these predictions. By the way, he thought most of his predictions were either unobservable in practice or were irrelevant, from gravitational lensing to gravitational waves. So, it's too bad, because he could have had a good career. I want to talk now about Robert Brandenburger, about mentors, because it seems like, again, yes, you're an outsider, but you're an insider. I mean, your mentor was one of the most preeminent theorists in our generation, right? Robert Brandenburger sat on my committee, found some errors in the wiring diagram of a 5-layer deep circuit schematic and a high electron mobility transistor. I don't know how he did that. Yeah, I'm kidding you. He did find some errors, which my advisor.
Cosmic string in your wires. Or
exactly. Yeah, I got some strings up in there. But speaking of strings, you give a much better description than almost any other description, maybe with the exception of him, of string gas cosmology. And it's started to make me think that I need to cover this in my chapter in my book, because I've been talking about Sir Rogers, conformal cyclic cosmology. We talked about that. We talked about Paul Steinhardt. We talked about the Burbages in the past, the steady state, basically. But it seems like string gas cosmology, which he did, kind of the week before BICEP results came out in 2014, he was like, I think the results are consistent with string gas cosmology. It turned out it was consistent with dust, not string gas cosmology or any kind of inflationary cosmology.
So dust gas cosmology is the new the Keating mechanism.
Well, I am pretty dirty, as you know, old, young, dirty, who would say. But thinking about these cosmological models, I want to turn now to cosmology from particle physics that we've been talking about. And you are an expert in this, and you have many ideas about the future and the past of the universe. And I want to ask, in that context, in that landscape, where does string gas cosmology fit in? Because I don't know that you're still working on it, or even if you ever really worked on it. It seemed like always kind of like a skunk works project that Robert was working on. But talk a little bit about this model and what makes it so appealing to you. And then I'll share some of my feelings about maybe testing it. But what do you think is so appealing about string gas cosmology that it warrants a whole chapter, a wonderful chapter in the book?
Mm-hmm. Yeah, into the cosmic matrix. That's the title of that chapter. So I did work. Part of my PhD dissertation was to extend string, because remember, in the early days of string theory, the fundamental degrees of freedom were just thought to be fundamental strings, and then when Polchinski came out with the D-Branes and Lee as well, they realized that there were non-perturbative degrees of freedom in the theory, which are hypersurfaces that strings can end on, called Dirichlet or D-Branes. And so the question is, if you look at this idea of string gas cosmology, you have to also consider D-Branes. And let me just say a basic idea of string gas cosmology. It's very kind of simple. So in the standard Big Bang cosmology, before we talk about, so there's no inflation in the standard Big Bang, hot Big Bang cosmology of Hoyle and others, which is that the universe starts off very much radiation dominated, and and it's hot and dense, and then you extrapolate that back to early times, and then you find you have a curvature and a density singularity at t is equal to 0, but then the solution basically smoothly expands, right, and cools. So if you think about the initial state of the universe, it's really just a hot, dense gas of radiation. So the idea of string gas is to just simply replace those particle degrees of freedom, which is a hot, dense gas of particles, okay, and the particle excitations of quantum fields, replace the early universe by a hot, dense gas of strings. And when you do string theory now in that context, what you find is that when you look at the density and singularity, actually, if you, for example, look at the density and the temperature, it no longer now goes to an infinity, but it reaches a bounded value called a Hagedorn temperature. And the density goes finite on you. So actually, you realize that the singularities that you would get in a hot Big Bang radiation-dominated particle-like scenario gets replaced now. Those singularities get replaced. They get regulated now because the string of degrees of freedom basically soak in all of those. I don't want to get into the physics of why that's happening, but basically the string degrees of freedom basically regulate that. And it has to simply do with the notion that strings are extended objects. And so if you try to zoom in, there are symmetries in string theory that basically tell you that when you zoom in, you end up with, it's as if you're moving in a big string again. So this is called target space duality. Physics of the very small now becomes physics of the very big. There's a symmetry there that strings enjoy that particles don't. So anyway, making a long story short, that theory in its early stages was that basic idea that him and Vafa, came up with this theory, said that there's a sense like a universe, a big universe and a small universe, and they're kind of dual to each other. They're related, interchangeable when you get to the Big Bang singularity. Now, the reason why I revisited this is that the story gets really interesting because if you start saying, well, what kind of cosmology is this? Is this a bounce that you come out of? So there's some pre-existing larger universe. And I was kind of using string gas cosmology to say that, okay, one of the things we might want to do, and I think Robert and Kummer and Vafa did this, was to say, let's try to build up a cosmology that is intrinsic to the theory itself. So let's not try to do inflation with string theory. Let's see what string theory says that's natural to it in terms of a cosmology. And it seems that this is the more natural thing, that if you start off with a hot, stringy early universe, it will naturally want to, do what string gas cosmology says it does. The other thing that was interesting was I used that, though, to motivate the question of, well, what really does happen at the earliest time in string gas cosmology? And this is where I brought in some ideas that actually, Bangs, Fischler, Susskind, and Schenker, the EFSS, had a way of reformulating string theory into something that Ed Witten called M theory. Now M will be matrix theory. That basically you give up, smooth the description of space-time, so space becomes very discrete. So you give that up. You give up the continuum as a principle. And I wanted to do this as a nod to Richard Feynman, because Feynman ends the character of physical law by saying, he talks about these principles, symmetry, energy, symmetry, invariance, and all these principles. And he says, maybe we have to give up one of these principles. And he did talk about giving up the continuum, but then he got stuck about, if you do this, you're screwed. But that's exactly what matrix theory did. It gives up the continuum in this interesting way. So it was a nod to Feynman, and then to say, okay, listen, if we now say string gas cosmology now goes into a matrix description, what would that look like? And I kind of end with that question. And then coincidentally, Robert Brandenburg and his students put a paper out literally saying that string gas cosmology is before there was that, there was a matrix. The universe is basically a non-commutative, discrete space-time, and then the smooth space-time emerged. So it's like an emergent cosmology, right? Which is very interesting, right? It lends itself more to ideas of condensed matter physics, right? Where things are no longer fundamental, right? But things can emerge, right? From fundamental degrees of freedom.
One most appealing thing to me is that it makes a concrete prediction in wild contrast to inflation, which is that it predicts a background of primordial tensor modes, but they are predominating at the smallest scales rather than the biggest scales. And, I wonder, because a theory like inflation, like string theory, has a certain, as you called it, herd mentality. It's not for me to call it that, but you're in the field, and that's you're right. And I can say I agree with that in a lot of sense, but I'm not a practicing theorist. Some of my best friends are theorists, though. But the point of my curiosity is that it's falsifiable, in that it could be ruled out and rather than ruled in. But again, in the back of my mind, I'm always wondering, are we too beholden to Karl Popper? Are we, as Lenny Susskind called him on this podcast, he called the paparazzi. It's not like Gödel, right? Gödel said,
that's great. That's really good.
Yeah, Gödel said, certain things are fundamentally not provable within a formal axiomatic set. But Popper was just like, yeah, it's good if you can falsify things. But, as my friend Stephen C. Meyer pointed out, astrology makes falsifiable predictions, right? I'm going to win the lottery tomorrow, or, tomorrow I'm going to find, true love if I'm single. Yeah, those are falsifiable. So now astrology is science. That's ridiculous. And hearkening back to what I said earlier about Maxwell and, if Twitter existed back then, and, he tweets out about the wheels and the vortices, and the Faraday did it and he was right, but, his successor in some ways, Maxwell did, and he was wrong. So I guess the question, that I want to kind of wrap things up on is, is there room again for for mainstream outsiders? Let me just make up a term, an oxymoron. Can you have something take the energy, the wind that's in the sails of string theory and inflation, the two dominant theories of particle genesis and cosmogenesis, respectively, and talk about, can you divert some of that energy intellectually to other pursuits? And even, if you could, how would that look? I mean, are you going to hire somebody, if a young Stephon Alexander came to your department right now, Brown University, one of the top departments in the world, 2 Nobel laureates on the faculty, including, and then plus you and Jim Gates. I mean, it's just like, so it's only grown since I've left, right? I think it was correlated by my leaving that you guys grew so much. But if a young Stephon Alexander, forget about the name, forget about all the cool stuff that you've done, recording jazz albums, Ryu, getting, leading the Harlem Gallery of Science, being president of NSBP, take away all that, take your name off the CV, take away all the struggles that you went through. Guy comes to you, gal comes to you, he or she says, here's my ideas, cosmic Vedic energy, alien dark energy. What do you say? What would you honestly do in that situation?
Good. I would not crush that spirit, but I'll do what I'm doing now, which is that I give a project that really lets them sharpen their and develop a solid skill set, mm-hmm. So they're versed in the tradition. And then I create a forum. I create an environment where my students and postdocs and those around, like there really is, you are encouraged to just say things and just use each other as soundboards. So it's sort of like, right, it's not a, but it also means that if you throw something at me, I'm gonna like. You should expect in a very playful way and in a way that is that's embracing. In jazz music, this Albert Murray, the great theorist, who mentored Wynton Marsalis and the brain behind jazz at Lincoln Center, called it antagonistic cooperation. Mm. You go to the cutting session and it's your turn to solo now, but the rest of the band, they're going to throw stuff at you. They're going to take you on a wild twist and turn, but it's coming from a place of, because I expect you to generate great ideas, wild ideas, and we're gonna take it seriously. But we're gonna tear it apart. Mm-hmm. And they're encouraged to do the same with me. I think really creating that where people are not shamed or stigmatized to say, to have ideas or be wrong. Okay, the idea of being afraid of being wrong. No, be wrong. It's okay. We can't make progress if you're not wrong. Mm-hmm. Otherwise, or staring a wrong thing into something that's right. And there's a thing of like who gets to be wrong, who's allowed to be wrong, who is not. Mm-hmm. Right. Mm-hmm. So kind of like democratizing that, who gets to be right and who gets to be wrong, who gets to speculate, who gets to theorize. Mm-hmm. I'll give you an example. Peter Warwick wrote he has a great blog. But anyway, just to give you a story about that, like he wrote a paper the other day about a version of basically gravity-weak unification, the idea that, you're told to not embed an internal symmetry like the Lorentz group. A space-time symmetry with an internal symmetry like those of the standard model. But he wrote a beautiful paper the other day.
Wait, why is that? Why are you told? What does that mean that you're told not to do that? Is that just like known not to work? Yeah. Like, is there some forbidden,
Yeah, there's a no-go theorem by Coleman and Weinberg, the Coleman-Weinberg theory. I believe this is Eric Weinberg, if I'm not, we can fact check that. Mm-hmm. The Coleman-Weinberg theorem has certain axioms, as you know, or a loophole. There are loopholes, of course, behind this. That says that if you take a space-time symmetry, like the Lorentz group, which is the rotation group plus, boost, so the group SO3, 1, you can take a subgroup of that, for example, right, and identify it with an internal symmetry like SU2. So SO3 is locally isomorphic to SU2. And so you can imagine thinking, maybe I can take this SO3 of the Lorentz group and figure out a clever way of saying that is the SU2 of the weak group. Well, I also played some of this game as well many years ago. It's like, let's break the rules. Let's break this no-go theorem and see, what the loophole is. And so anyway, he recently wrote a paper that was really, also technically very strong. And so, what I did? I mean, I invited him to give a seminar at Brown, a theory seminar.
Yeah.
Because I sort of feel like, like we need to hear from him, right? And this idea of like democratizing who gets to be heard, who gets to, to speculate, who gets to break the rules is, to me, something that I'm having a lot of fun with these days.
Mm-hmm. Yeah, right. If you look at, Wolfgang Pauli and you say, sorry, you can't speculate, on the conservation of energy as sacrosanct, and you can't order another particle. If you'd said that to him, I don't know if he would let you do that. But anyway, the point is, we don't know where the right answer is going to come from. And, I think it's like walking that dichotomy of being enough of an insider that you know what happened in the past so you can respect the great. Because the one thing that shines through in this book is that you are a scholar. In other words, you study not only the subject matter of the equation, the history, the milieu, the cultural milieu in which these things were developed. And that's part of being a master. That's part of being an expert, in my opinion, at least. And you embody this trait that I've spoken about many times in my book, even the word scientist in Russian, that I learned from Alexander Polnarev, your friend.
Yes.
Alexander and Alexander, those great papers. But the notion of the word scientist in Russian means someone who is taught. And to me, to be a good teacher, you had to have been a good student. And to be a good teacher, you also have to teach people in the future. And so, I do, I give you incredible accolades and really much respect, because you're not just content at doing the calculations. You're bringing people up. You're inspiring the youth. You're the president of the National Society of Black Physicists, leader of the Harlem Gallery of Science, the Hip Hop Museum. Let's talk a little bit about those organizations for a little bit. Why is that important? I mean, I've talked to you about this. You and I are brothers, right? I say, why are you continuing to pay the black tax? In other words, you are working your ass off harder than I am. I don't have to opine on, how do we bring up the next generation of underrepresented men and women, the next generation of leaders. I don't get asked to do that because I'm white. You have to pay this tax, and our female sisters in science, they have to do it because they're women. I don't want to get too woke about it, but that's true, right? I mean, you have an excess burden that I don't have to do, and you go above and beyond it. Why do that? Why? I mean, don't you want to get to the heart of the matters in the universe and get back to your research?
Mm-hmm. Yeah, so it's a dance, and I think after my tenure as NSBP president, I will, I have to get back and devote time, because time is limited, time is finite, and so it's kind of selfish, because actually, I get really I gain a lot of pleasure from watching and seeing, especially students. One of the things I really do enjoy still doing is that, with NSBP or the Harlem Gallery of Science, just talking to students and talking science with them, and getting, sort of watching them develop their superpowers. Watching them, come back, you learn how to do a Jacobian transformation, and they get a kick. There's something really cool about engaging in that process. The other thing too is that it's selfish, because sometimes I rely on them to throw things at me that I would never think about, because they're coming at things from a beginner's mind perspective, right? John Coltrane would say he wished he had the ears of a baby. He wished he didn't know too much music theory, because then he could listen to music in the purest, most pristine way, there's something, there is a part where I really do get a lot of joy out of that. In terms of the Harlem Gallery of Science and the Hip Hop Museum, the Universal Hip Hop Museum, where I will be leading the STEM initiatives in the hip hop. Well, I was one of those kids, and growing up when hip hop music was being developed in the '80s in the Bronx, doing that part of the hip hop evolution coming in from the '70s, and we were behaving like scientists. We were taking a digital sampler, and modifying it, right, to sample in ways and sample things that it was never really designed to do. And Grandmaster Flash was basically studying the moment of inertia, of different types of turntables, to designing new types of crossfaders and the electronics for that. So, like, just the idea that the content and the what's the word, like, the experimental tools that we that are the objects, okay, of scientific inquiry, the palette is much larger than just like being at a blackboard with chalk or being in a lab, with an amplifier. It can look like, electronic music. It can look like, breakdancing. It can look like, the rhyme patterns of a flow of. So I think that, the patterns of different polyrhythms and what that has to say about geometry. So I think that we use the idea that we can use these ways of engaging really bright and promising young people and show them that there's science there too. There's amazing physics and chemistry and biology and electronics and those things that they're so interested in, and use that as a rabbit hole so that they can express whatever it is, whatever song they're going to play in their scientific career. I think is what's actually exciting about those engagements.
Yeah. Well, Professor Stephon Alexander, president of the National Society of Black Physicists.
Servant, humble servant.
Humble servant. I heard it said by one of the past presidents that you're one of the best presidents they've ever had. I'm not going to get into the details because I don't want to get you in trouble. But anyway,
well, one of my favorite hip hop groups is a group called Dead Prez.
I want to ask you one final question, because we played Into the Impossible in the past, where I ask you these existential questions. I just want to ask one this time. You get one bite at the apple this time. You and I are both 50 now. By the time this comes out,
not a bite of the dust. Not another one bites the dust. Like that.
No, we're not going to do that. We're not going to talk about my sequel, my next book, A Farewell to Arms. Another one bites the dust. I want to ask you, 50 years from now, 10 to the 50th years from now, let's just say 50 years from now, what one chapter would you most like to have the answer to? In other words, this book is full of puzzles and mysteries, of conundrums, of questions. There's nothing solved in the sense that, like, you're just describing the double slit experiment for the 50,000th time. No. That's not what this is about. This book is about a manifesto, a challenge to future physicists, the same way that Hawking ends with, if we can get, a theory of everything, we'll know the mind of God. I happen to dispute that. But anyway, of these, 9, 10, 11 chapters in this wonderful book out now from Basic Books, shout out to TJ Kelleher, who is, I've known him for a long time.
The greatest editor in the history of the universe, of universes.
Yeah, I mean, I've had on so many Basic Book authors. He owes me a bottle of Blue Bottle coffee or whatever you guys drink over there on the East Coast. I want to ask you, of all the chapters in this book, what would you most be curious about? Come on, it's like my mom. You met my mom, and I'd always ask her, Mom, who's your favorite kid? I've got 3 brothers, and she'd say, oh, that's like asking me to choose my left hand or my right hand. I said, Mom, you're left-handed. I mean, come on. Of course you're going to choose your left hand. Of course I'm your favorite. No. But I want to ask you, there's got to be one thing in here that, that's equal but above equal. What question do you most want to know the answer to, if you'll permit me?
Yeah, so, it's funny you say that. I'm looking at a chapter, and this chapter was related to actually a crazy woo book I was reading as a grad student. And it was a book called Zen Mind, Beginner's Mind by Suzuki. Yeah. And so I have this chapter called The Zen of Quantum Fields. And maybe can I read just one section of this?
Yeah, of course.
So, and let me see if I could. Yeah. So it goes, my first introduction to Eastern philosophy was a book entitled Zen Mind, Beginner's Mind by Zen Master Shunryu Suzuki. And Suzuki had a most interesting metaphor for existence. Imagine a stream flowing towards a waterfall. When the water leaves a cliff, a droplet of water leaves the stream and at some point rejoins the stream. Life is like that droplet of water, and the stream is like the universe. During the time between when we are born, quote unquote, and when we pass away, quote unquote, we are like the water droplet, feeling like we are separate from the universe as a whole. But before we are born and after we die, We are part of the stream, the universe. I remember wanting there to be some truth to Suzuki's metaphor. So in what way could we be connected to the universe in the poetic manner described by Suzuki? And so I use that metaphor, and I end this chapter before I go into talking about quantum field and why quantum field theory is kind of saying something like this, right? Again, metaphorically. And I end with the last paragraph of that chapter after going through quantum field theory in that sense. And I say, consider electrons in a star millions of light years away from Earth. While there are many electron particles, there's only one electron field that they are born from. Those electrons and the electrons that are in you and me were created as quantum excitations from the same universal electron field in the early universe. In fact, every other particle, including quarks and neutrinos in the universe, are quanta that emerge from their corresponding field vibrations. It's in this Suzuki sense that we are tethered to the fundamental fabric of the universe. Anyway, so again, it's as you said, it's one of these dream ideas, but are we actually connected to the universe in this poetic manner, right? And it seems that the lessons that we're learning of this oneness and this wholeness is not just maybe woo-woo, but actually closer to the picture of, say, quantum field theory and the early universe that we're trying to discover, trying to learn, and you are trying to experimentally probe. How's that?
That's great. That is great. Well, Stephon, my oldest, dearest friends, one of them, top 2 or 3 that I've known longer than anybody, even than my wife. I want to thank you for this book because it is a gift. It's mesmerizing. It's inspiring. It's thoughtful. It's soulful, and of course, it has a hell of a beat and has a hell of a rhyme to it. And I just want to thank you for kind of rekindling this love in me of the big question. That's why I got into being a physicist. I may be a different reflection of it in that I'm an experimentalist, but you and I, going back to 1993, we first met each other. I just can't believe that you have that you remember these things that we've gone through and that have really steeped in you this unique approach to science. I want to thank you, and I want you to give my regards to Professor Griff, Flavor Flav, no, Chuck D. I'd love to meet that man, and maybe
maybe we could all do something with Chuck. Maybe we can do something with Chuck in the future.
That would be fun. I'd love to get him on the podcast with you. And
can I say one last thing?
Yeah, go for it.
Yeah. I also, again, this book, the thing about Fear of Black Universe, it was like think about quantum superposition. It had many different superposition, different types of meanings. Mm-hmm. One of it actually was my fear of kind of coming out clean and say, look, I got into physics because I had these bigger questions about my existence. And I think, some of it is your fault because when you wrote your book, writing your book and you kind of coming out and talking about God and talking about these matters, okay, as well as your physics, and so in connection to your physics. I think it was a thing. It gave me the hall pass to write my book. So I want to thank you.
All right.
For that.
I will take your encomia, your blurb, which you were kind enough to put on the last book that I wrote. And you feature also in my upcoming book as well, but we'll save that for another time. Professor Stephon Alexander, Professor Brown University, theoretical physics, cosmologist, saxophonist. You want to take us out with a little riff, or are you the reed?
No, what? The reed fell out of my.
No. All right. I'll put in some Public Enemy. I'll try and get some rights-free. Fight for your right to party, a party for your right to fight. I want to thank you, Stephon, for sharing some of your time.
Welcome to on sax. Yeah. Okay.
All right, my friend. Thank you so much.
Any sufficiently advanced technology is indistinguishable from magic.